Okay, I'm going to make a start now, ladies and gentlemen. Well, good afternoon and welcome to this CIREM webinar organised by the Southwest Branch and supported by the Met Office and the EA. This is in fact the third and final webinar that the Southwest Branch and Met Office have created as a precursor to the COP26 Climate Emergency Conference that is taking place in just over 10 days' time in Glasgow. A few words on housekeeping first though. If you experience any technical issues and need assistance, please use the chat to let us know what the problem is and what help is required. We will take questions at the end of the talks. Please use Slido if you would like to put a question or make a comment or cry for help. And you can open Slido feature by clicking on the Slido icon, which is an S at the top of the screen. When asking your questions, please state who you are posing the question to. We've got 5 speakers today, and we're going to be running literally back to back. Now, 1.5 hours CPD is attributable to this webinar. However, we do not provide certificates for the event. Just a little bit about CIREM Southwest. Well, we are in the Southwest. We are proud to be here, and we're proud that the Met Office is also located in our region, and we're working closely with the Met Office as we have done to set these webinars in position. Now, CIREM has had to switch to the virtual world, hence today, and we're reaching out to a global audience, providing relevant and accessible events to our community working in the water and environment sector. We are therefore connecting local, national and international through our digital series. We would just mention that this event is a precursor to the COP26 in Glasgow. The COP15 event, which was happening earlier this year, is actually put back to provisionally April next year. So there will be more information on that in terms of what CIREM are doing in supporting. I'm going to move back to this event though, and thank you for attending. This webinar considers how we incorporate climate change in flood risk management, and we have 5 key speakers, all specialists in their subject area. First, we will hear from Lizzie Kendon, Science Fellow and Manager at the Met Office, with a presentation on short duration precipitation and implications for flood risk in a changing climate. We will then hear from Caroline Sutton of the EA with a presentation incorporating climate change in land use planning strategy. Ben Meredith of the AA will then present on the impacts of climate change on coastal flood risk, very important to us in the Southwest. Then Claire Waller, EA Senior Advisor, will present on the impact of climate change and peak river flows. Finally, Mike Vaughan, EA Senior Advisor, will summarise considerations of climate change in real-time flood forecasting. So, just a final note, there will be some links into various events that will be put into the chat that you can access after the event, but I'm now going to hand over to Lizzie, who will talk about short duration precipitation and implications for flood risk in a changing climate. Over to you, Lizzie.
Thanks. I'm just trying to share my, hopefully this will work. Sorry, it's just taking a minute to load up.
Don't worry. This is the wonders of the virtual world.
If this doesn't work, I can just share my screen.
That might be.
That might be easier, might. Okay, okay, let's forget that. I'll just load up. I'll just share my screen directly.
Okay.
Okay. Now, can you see my screen?
Yes.
Is it okay? So shall I? Are we all good to start?
Yes. Off you go.
Okay. Okay, hello everyone. So I'm Professor Lizzie Kendon. I'm at the Met Office, where I lead a small team of people using very high resolution models to study climate change, and recently released a set of climate projections called UKCP Local, which people may be familiar with, which is kind of the first time we've released national climate scenarios at such a high resolution. And today I'll be talking about some results from those and the implications for flood risk. So what are the UKCP Local? They're a new set of 12 climate projections using a model as detailed as that typically used for weather forecasting. So this is the first time that we've released national climate scenarios at this scale. And this is really important because these models are much able to better capture rainfall, especially on very short timescales. So hourly rainfall, for example, and right down to local scales. So these set of 12 projections have a 2.2 kilometre grid spacing across the UK. That compares with the more traditional climate model, which has a grid spacing of the order of 10 to 100 kilometres. So they're a lot more detailed. We have 12 members, and data has been released for three 20-year periods, 1981 to 2000, 2021 to 2040, and 2061 to 80. It's important to say that this is for the high emission scenario, RCP 8.5. So all the results I'll be presenting today relate to that scenario. And that was a deliberate choice to have a really strong signal to noise, but there are methods that we can use to provide information for lower emission scenarios too, but that's not something I'll particularly be covering today. So these projections were updated just this July, and they're allowing us to provide new estimates of changes in hourly rainfall and daily rainfall extremes. So we can look at storms, summer downpours, also severe wind gusts, and the information is at a scale that can feed directly through to hydrological impacts models, so we can look at flooding. Now, one of the key things when we're looking at climate models is how credible they are for what we're particularly interested in. And we try to assess to what extent they give a good representation of the underlying processes. And here these figures here look at return levels for different return periods from 2 years out to 100-year return periods for the different seasons for hourly rainfall extremes. And kind of the curve here, which we term as the growth curve, is very important because that is giving us a sense of the extent to which kind of extremes become increased in intensity as conditions become more favourable. So, how much the return level increases as a function of the return period or rarity. So that is giving us a sense of whether the model is able to actually capture some of the processes that are important, and then whether we have confidence in the future projections. So in this case,
Lizzie, can I jump in there? Your slides aren't progressing.
They're not progressing.
No. Well, a number can only see number 1.
You're still on the title, it's still on the title slide.
Yes. Yeah.
Okay, I don't know why that's the case. So they are progressing for me. Okay, let's try something here. That's very annoying. Okay, let's do it this way. Okay, so I've just discussed that slide. Sorry. That's progressing now, presumably.
Yep.
We can see number 3. Yeah.
Okay, I don't know what happened there. I was progressing it on what I was looking at, but it wasn't working. Okay, right. Sorry. So, okay, so I'll start. Hopefully you can see this now. So we've got basically what we can see here is the in black here are the observations. So these are the CH gear observations of hourly rainfall, and what you can see is that as you go up in return period, of course, the return levels increase. And then if you look at the different colours, these show different model outputs. So in red here, we have the convection permitting model. So this is the model that is used behind the local 2.2 kilometre projections. And in blue is a 12 kilometre regional model, which is more traditionally the sort of resolution we'd use for climate projections. And that is what actually indeed drives the local 2.2 in red. And what you can see is that in red, the local projections very nicely overlap with the observations, and they follow this growth curve very well. Whereas in blue, the 12 kilometre projections don't capture it. They indeed showed a too rapid an increase in return level with increasing return period. So, so basically what we think is going on here is that when you're looking at hourly rainfall extremes, they're not particularly reliable in these coarser models because some of the assumptions that go into those models to try and capture convection break down when we're at these sort of hourly timescales, and so we're not capturing the correct variation of return level with return period. Whereas the 2.2 kilometre model actually does a very good job, and therefore that gives us confidence that we can use them to project future changes. So, so here are some results actually providing what future changes these models suggest. So in this case, we have return levels from 2 years, 30 years up to 100 years. We have the present day return levels, and then we have future changes or uplifts in those. And in this case, there's a low estimate, a central estimate, and a high estimate. So if we look at the bottom row, for example, the 100-year return level, we have a UK average uplift of about 12%, a central estimate of about 28%, and an annual average uplift as a high estimate of 46%. But there is some spatial variation in that, with greater increases in the north and the south. Now, how did we come up with these? So we used the UKCP local projections, and we combined that with an advanced statistical model. In particular, this is a spatial statistical model, so it allows us to fit the extreme distribution, if you like, to all the data spatially at the same time to give much more robust estimates. And also we have here the 12 ensemble members, of course, and that is allowing us to have some measure of uncertainty to be incorporated alongside the statistical model uncertainty. And that's what ultimately is allowing us to provide these low, central and high estimates. Now, we have worked with stakeholders to look at what future periods, for example, are needed, what seasons are important, and so on, and what return levels are important for stakeholders. And so we've been providing information on uplifts for stakeholders and as part of the future drainage project. So if we then look at how these results compare to existing allowances for peak rainfall intensity, so these are estimates for the 2070s. So the new estimates for the 100-year return level are shown in red. So again, I should emphasize these are for the RCP 8.5 scenario, which is a high emission scenario. But you can see, compared to current guidance, the values here in red are considerably higher. So they're higher than what would be being provided for the 2080s, even though the baseline is actually more recent. So they're quite a bit bigger, both for the upper and the central estimate. So this is really identifying that maybe there's a need to revise the current guidance for uplifts for peak rainfall intensity based on these new UKCP local projections. We also have done some work looking at specifically exceeding 30 millimetres an hour, which is a threshold used for triggering flash flood alerts. And you can see that in all the different regions here, there's roughly a doubling of the frequency of exceeding 30 millimetres an hour locally. So that's a really big change by the 2070s under this scenario. So the Future Drainage Project is a collaboration between Newcastle University, the Met Office, University of Exeter and JBA Consulting and others. And in this case, we're taking this new capability from the local 2.2 model and feeding and calculating these uplifts, which I've shown for various different return periods, and then feeding that information through into flood modelling to try and provide information on what's needed for current design standards, for example, and what sort of flood inundation levels we might expect with these new results. A set of guidance was released in July to coincide with the launch of the UKCP local projections. And this provides information more about these uplifts that have been provided. Just to say, the uplifts differ by the location, the rainfall event duration, the return period and the time horizon. So information is provided for all of these. And again, we have this central and upper estimate of the change provided. So there's the link there for where you can get the guidance document and how more information on how to get those uplifts. Now, if we, here's a kind of preliminary result of what this actually means in terms of flooding for London, as an example. So here there are two maps presenting flood inundation for the present day, the 2050s, and then on the right hand side, the 2070s, with the kind of central estimate shown in sort of darker colour and the very dark colour being the upper estimate. And so these are using these new UKCP local uplifts to provide information about flood levels in different regions. And this is work that's going on as part of this future drainage project. So another interesting aspect of the change in the UKCP local projections is that we see a change in the seasonality of extremes. So the results I was just showing you previously all relate to uplift for annual extremes, but if we then start to pick it apart in terms of the seasonality, I think there's some very important results here that need to be taken into account. So in red here is the convection permitting model, this 2.2 kilometre model, and the solid bars show the frequency of extremes in the different seasons in the present day. And you can see, hourly extremes at the moment generally occur in summer season, with some in autumn and very little in spring and winter. And that's borne out by the observations too. But then if we move into the future climate, so what we term here time slice 3, sorry about the jargon there, but if you look at the bars that are kind of have this circle hatching on them, that is the distribution for the future, for the 2070s period. And you can see that now there's such a very large increase in hourly extremes in the autumn that the distribution has shifted such that autumn now becomes the season when we get most of these extremes. And that's likely to be really important and something that needs to be taken into account, because obviously it's autumn where we see leaf fall and potentially blockage of drains, which can be a major factor in flooding as well. So I'm currently doing some work with Bristol University, where we are trying to pilot using the UKCP local projections, but this time instead of just looking at uplifts provided as the approach we're using in future drainage, we're actually trying to use the full hourly rainfall time series. So not just looking at changes in intensity, but also the frequency, the duration, the clustering of changes in time, and what that means for pluvial and fluvial flooding. So we're going to be running the time series data is going to be going into the Decipher river flood model, and then that's going to be fed through to ListFlood to provide information on flood levels. And we're doing it for 3 near natural catchments and 2 urban catchments. And what we're trying to assess here is to what extent sort of the existing approaches used in flood modelling, so applying a climate change factor to a design storm and observed time series, are robust, or whether we really need to capture the real details and the full changes of the time series as captured by this local 2.2 kilometre model. And it'll allow us to look at the relative importance of compound events, for example, the importance of the antecedent conditions and other aspects, as we see how as those pan out and are manifested in the hourly rainfall time series. So one thing that's important to note is that these UKC local projections are just part of a suite of models from UKCP 18. And these models, although they're the first time really we've been able to release anything at these sort of spatial and temporal scales, they only sample some of the uncertainties. And that's illustrated here. So this is just looking at the mean responses of summer temperature, rainfall, winter temperature and winter rainfall in Scotland and England. And the black bars and whiskers is the full probabilistic projections released from UKCP 18. And then the blue dots are the CMIP 5 models. So these are different models from different international centres. Then in yellow, we have the Hadley Centre Global Model, which is driving the regional model in pink and onto the convection permitting models in green. And you can see basically for these sort of mean statistics, the local model is following the driving model. And so really in summer, we're only really sampling the warm and relatively dry responses. And it's important that people are aware of that. So we aren't sampling the full range of uncertainty. And one interesting response, which I'll mention briefly, is on the bottom right. You can see that there's some green dots there, which are outside of the range from the full probabilistic projections. And that was something we didn't expect. So we looked at this a bit further, and we want to try to understand why increases in mean precipitation were so much larger in the local model than in any of the driving models. And what we found actually is it seems to be related to a very sharp land-sea contrast in changes, which are seen in the coarser models. You can see that on the bottom panels here. This is the 12-kilometre response, and for frequency of rainfall, there's this very sharp land-sea contrast, where we've got increases in rainfall frequency over the UK in winter, over the sea regions in winter, and not much of an increase in the frequency over the UK land. And this is down to how showers are triggered and advected in land in these models, and essentially deficiencies in the convection scheme that's used in all the coarser models. And it's only in these convection permitting models that we're able to fully advect showers in land, and that's obviously an important signal here in wintertime. So just to say that we have run convection permitting climate projections over the Europe as a whole. So here, this is showing, unfortunately, the animation doesn't seem to be working, which is a pity. On the right-hand side there, the convection permitting model, you can see this, the domain of the model. And then at the bottom there is the 25-kilometre model that drives it. And what you see is that the intensification of rainfall is quite different in the local in the 2.2-kilometre model, and also the diurnal cycle is much better, and the kind of intensification of rainfall as it enters the domain. And this is really giving us confidence in these sort of model projections much more widely, and is allowing us then to look at sort of events like we saw in Belgium and Germany recently. So you may remember that in just this summer, this was very severe flooding to hit Belgium and Germany, and it was particularly related to a slow-moving storm, so a storm that came up from the south and kind of settled over that region for a couple of days. And so we've been doing work using this high-resolution model to look at these types of storms and the extent to which we might expect more slow-moving storms in the future over Europe, including over the UK. And we do indeed find that there could be a really big increase, so a 14 times increase in slow-moving storms over land in future, and that's a very big change and has very big consequences for kind of flooding, because eventually it's those types of events that lead to very prolonged rainfall amounts. So just the very last slide. I'm conscious I'm running out of time. So what can users expect over the next few years? So I mentioned this issue about the uncertainties and the extent to which the UKCP local is only capturing some of the uncertainties. Now, we are planning now to run a set of experiments downscaling different global models. So some of those CMIP 5 models will be downscaled using the local 2.2-kilometre model, and that will give us a much better estimate of uncertainty in changes in local weather extremes. And the other thing is we're actually filling the gaps. So we've provided data for these 3 20-year periods, but we're now filling the gaps. So hopefully fairly soon we'll be able to release information providing changes for the full transient evolution. So for the first time, really, we can look at how climate's going to evolve from 1980 right out to 2080, 12 realizations of that with data every 2.2-kilometre grid box and every hour by hour. So that will be an amazing source of information to allow us to look at kind of how our climate's evolving and how we're going to be, basically the climate signal is going to be emerging through time. Also, we're working to improve the models. We're constantly doing that, and there's a few key aspects that I can see will improve over the next 5 to 10 years. Firstly, the representation of soil groundwater, which is important for improved runoff and land atmosphere feedbacks, particularly is critical actually over Central Europe. Also, we're bringing in ocean coupling so that we can look at combined hazards at the coast. So the combination of very heavy rainfall and river flooding combined with a storm surge. We're also hoping to bring in scale-aware convection, which has allowed us to have a much more consistent climate model system from the global right down to the local scale, and would reduce hopefully any of the remaining precipitation biases due to these models essentially requiring updrafts to occur at 2.2 kilometre grid scale, whereas in fact, obviously, they can occur much smaller than that. And finally, we're hoping to do quite a bit of work to synthesize information from these new kilometre scale projections with a wider sampling of global models to give better estimates of present day and future risks. So what I mean by this is we have a relatively small ensemble, 12 or so very high resolution projections. Then we have a lot more bigger ensembles of global models, CMIP6, for example. How do we combine all this information? What should we be using when we're interested in changes in local rainfall extremes? And there are nice statistical methods, including machine learning, where we can use the kind of cascade of information to augment the information at these very local scales. And that's something that we're working on at the moment. And with that, I'll stop there. Thank you.
That's very helpful, Lizzie. I'm just wondering, you've got the slide up there on your personal pledges to reduce carbon, which I think is probably as relevant to the discussions that have taken place this week and will take place in COP26. Could you just hold them there for a second? Because I think personally, I'd like to just look at those for a second and take stock of those, because I think those are excellent personal pledges that we can all consider. I'll give a few seconds for that to sink in. I just wanted to check, Lizzie, do you have to dash off, or are you going to be able to stay around for questions and answers at the end at about 2:15-ish?
Yeah, I can stay till 2:50. Yeah, that's fine.
That's fine. That's absolutely fine, because your presentation is slightly shorter than I was expecting. That's fine. That means we'll probably have the question session nearer to 2 o'clock than 1:15, which would probably help with everybody's busy schedules. Right, thank you, Lizzie. There's a lot of information there, and I appreciate that. And I'm hoping there'll be some questions coming through the chat via Slido. I'd like to now invite Caroline to get prepared for her presentation. And this is the first of 4 EA speakers. And just to recap, it will be a presentation on climate change and land use planning, strategy and allowances, i.e. how does climate change impact on land use planning? I think you're ready to follow, aren't you, Claire?
Yep. Yeah, Caroline. Hi, everyone.
Sorry, Caroline.
No, it's okay. We don't want people to get confused later when Claire comes on.
Absolutely.
Hi, everyone. Yeah. So I'm Caroline Sutton. I work at the Environment Agency, and I lead on spatial planning and climate change allowances. But before we can go to the next slide, please. So just before we launch into our climate change work, just a bit of a summary really about what the Environment Agency does. Obviously, I'm sure a lot of you work with the Environment Agency are quite familiar, but it's always helpful to have a recap. So there's sort of 3 core strands on this slide. We help people and wildlife to adapt to climate change and reduce its impacts. So right at front and centre is climate change of our sort of overarching what we do. We also work to improve the quality of our water and land and air by tackling pollution. And we work as part of the DEFRA group to create a better place for people and wildlife. Next slide, please. So we have a corporate plan called EA 2025. As part of that, there are a number of ambitions, and our climate ambition, again, is front and centre of that. And core to that is to create a nation that's more resilient to climate change, or resilient to climate change, should we say. Next slide, please. Moving on to our National Flood and Coastal Erosion Risk Management Strategy. Hopefully you'll be familiar with this. We updated it in the last couple of years, and so it's something that we've been promoting very heavily recent years, so hopefully you'll be familiar with it. The vision of the strategy is a nation ready and resilient to flooding and coastal change today, tomorrow, and up to the year 2100. As you can see on the image to the left there, the sort of core pillars to that, and influencing placemaking is important to that in terms of how we influence how places evolve, how new developments and plans for new development, new places evolve and are designed. In doing that, the key theme will always runs through our whole strategy is around what resilience means. Resilience to climate change doesn't necessarily mean traditional flood and sea defences. They are important, but we can't necessarily build our way out of the future risks that climate change might bring in some places. So the strategy sets out a framework for resilience that uses a range of tools. So alongside using traditional hard defences, other tools are promoted, like natural flood risk management, so introducing river meanders, reforesting upland areas, and using green infiltration suds, and also things like property level flood resilience that help to keep water out of buildings should flooding encroach upon them, and if they do flood, design them in a more resilient way so you can recover more quickly after a flood event. Next slide, please. Another core part of planning for a more resilient future to flood risk and coastal change is adaptive approaches and adaptive pathways. Adaptive pathways are about managing uncertainty and climate risks by building in the capacity to change and adapt through time. This relies on assessing a range of climate scenarios and having a plan in place to monitor, review and adapt depending on which climate scenario materialises through time. An adaptation pathway is delivering actions to manage the short to medium term climate risks while keeping other options available to allow adaptation and resilience to longer term risks to be built as we better understand how climate change is evolving and how it might affect us. The key to the success of this is obviously that ongoing monitoring about the pace of climate change, but also making decisions at the right time and investing in mitigation and resilience measures at the right point in time. So we're not doing it too early and definitely not doing it too late. Next slide, please. Just a few examples of adaptation pathways. We've got a 200 million resilience innovation fund, which is delivering 25 pioneering projects around resilience and flood risk resilience. £8 million of that is being spent on an adaptation pathways project. This slide shows the location of 4 projects that are specifically delivering adaptation pathways. There's more information on gov.uk, and in the slide notes there is a link to where you can find more information about that. And also Ben later in his slides is going to cover an example as well, so we'll get to hear a bit more about that in a few minutes. Next slide, please. Moving forward in terms of how we account for climate change and help people account for climate change in planning. As you all know, the climate is changing, and there's going to be a range of impacts that will increase flood risk and drive coastal change. There are some quite startling statistics that are on the slide there, which I'm sure many of you are familiar with. So in order to help do this, we provide climate change allowances guidance. You might be familiar with one or both of them. We provide guidance for flood risk assessments. Again, there's a link provided in the notes. This helps ensure development is designed to be safe from future flooding risks. And also climate change allowances for FCRM projects, schemes and strategies. So this is for the guidance we apply when we're understanding how to design our flood risk management schemes to ensure that they're resilient to climate change. And again, the link to that guidance is included in the slide notes. Next slide, please. So in terms of the climate change allowances, they're very similar between the two pieces of guidance, and I'll highlight where they're different. We provide climate change allowances for various flood risk parameters. So for sea level rise, our current sea level rise allowances are based on UK CP18 high emissions scenario using the 70th and 95th percentiles. The wind speed and wave height allowances are unchanged since UK CP09. However, evidence in UK CP18 did not trigger the needs for these to be changed. Although in our recent edition of our guidance, we've made changes to make them easier to understand and apply. The storm surge allowances, these have been updated recently and are based on UK CP18. The rainfall allowances, they're still the allowances we've been using for some time, as Lizzie highlighted in her presentation a few minutes ago. We have a national rainfall allowances at the moment, and now we have the information in UKCP local and the future drainage research as well to help us update those, and that's something that we're working on at the moment. We've also got peak river flow allowances as well. These are based on UKCP 18 high emissions scenario, using the 50th, 70th and 95th percentiles. Just to introduce what the high emissions scenario is, it's RCP 8.5. RCP stands for Representative Concentration Pathway. An RCP is a concentration of greenhouse gases. So they're comparable to UKCP 09, but not exactly the same. So basically the high emissions scenario is a high amount, a high concentration of greenhouse gases. So we're using effectively the most extreme end of the scenarios presented in UKCP 18 to base our climate change allowances on. The RCPs very helpfully can be equated to a change in temperature by 2100, and RCP 8.5 roughly equates to a 3.2 to 5.4 degree increase by 2100. Next slide, please. So I just thought give you a couple of slides on what the climate change allowances look like. These ones are for sea level rise and offshore wind speed and wave height. The storms, they're all based, so basically the storm surge wind speed and wave height allowances are set at a national scale. So there is one set of allowances to apply wherever you are in England. So it's important to note this guidance is for England, not for the whole of the UK. For sea level, the allowances are provided for different sections of the country, loosely based on river basin districts, and that's all explained in the guidance. That you can see the link there on the slide. We provide those allowances, broken down to be able to sort of represent the change that we see as you go around the coastline in different parts of the country. There is a key difference between the guidance for flood risk assessments and FCRM schemes, in that the FCRM schemes guidance actually directs you to go directly to UKCP 18 user interface to obtain the 12-kilometre grid projections. So a much more finer grain of precision there. However, we feel that for the purposes of flood risk assessments, providing them for the river basin districts provides an approach that is firstly simple and easy to use for the thousands of flood risk assessments that are produced every year, but also represents the research and findings and projections in UKCP 18 in an effective way. Next slide, please. This slide just shows the allowances for peak river flow and peak rainfall. There's been a change in how we present our allowances for peak river flow. Previously, we provided allowances for peak river flow for 12 river basin districts. Now we provide them for 93 management catchments. So the top one here shows an excerpt from our new map of peak river flow allowances. You click on the location or use a postcode to find your location, and it shows you the management catchment and the allowances associated to that management catchment. For peak rainfall, the allowances are national, and as I pointed out before, but hopefully with time we will be able to better provide updated allowances that represent some of those regional differences that Lizzie showed us in the presentation before. So that's something to look out for in 2022. For all of our allowances, we provide allowances for different epochs as well. However, for most developments, when you're thinking about land use planning, we tend to use the epoch which is towards the end, so planning for a 100-year lifetime. So the 2080s epoch is generally the one that's usually applied. And what we do is we advise that these allowances are used as part of design flood assessments. And Ben and Claire will explain a little bit more about how they're applied in their presentations. Next slide, please. So moving on to how they're applied in planning, planning policy is really clear that inappropriate development in areas at risk of flooding should be avoided by directing development away from areas at higher risk, whether that's now or in the future. And where development is necessary in areas that are at risk of flooding, they should be made safe for their lifetime without increasing flood risk elsewhere. So what this means is it's important to account for how climate change will affect flood risk when thinking about where to locate your development, so choosing those areas that are at lowest flood risk, when designing flood risk mitigation to keep your development safe from flooding, but also when designing flood risk compensation if you're developing in an area at risk of flooding and you're effectively moving water away from being able to flood that place. You need to be able to provide compensation to ensure that flood risk isn't increased downstream. And when doing that, you have to account for climate change for that as well. Our guidance advises you do this by assessing a range of climate change allowances for sea level rise and peak rainfall. For peak river flow, we advise use of the central allowance, except for where essential infrastructure is involved, and also we advise use of the high essential for strategic flood risk assessment, so you get that picture of risk for your whole area, thinking about how that might change in high risk locations. We also provide allowances for assessing extreme or credible maximum scenarios. These tend to be used mainly for nationally significant infrastructure projects, and there is a requirement in the national policy statements for nationally significant infrastructure projects to assess these worst case scenarios. And so they're used for that. They're also used, we also advise they're used for urban extensions or creating new communities in places where there isn't an existing community, because it's really important where you're introducing a community to a new place that you really consider that potential worst case scenario around future flooding risks and make your decision in the knowledge of those risks rather than without that knowledge. That was all I was going to cover for now, and I'll hand over to Claire.
No, you're handing over to Ben. Hopefully,
oh,
you're
Ben,
there,
sorry.
That's all right.
Ben.
I'm in ready. That's fine. Okay. Hi, everybody. So my name is Ben Meredith. I'm a coastal risk advisor in the Environment Agency. Over the next few minutes, I'll present an introduction to the coastal aspects of the UK CP18 data and what that means for our coastline, as our coastline is arguably one of the most sensitive receptors to the impacts of climate change. I will then demonstrate how we use those projections in our coastal modelling at the EA, and I'll also be touching on some of the wider impacts of risk rather than just solely flood risk. So if you could have the next slide, please. So the UK CP18 Marine Report details the work that was done under that project and to assess the impact on our oceans. The overall trend shows increases in sea levels, but there are variations between the different levels of atmospheric warming, and we see a range of impacts around the country. And the diagram here just shows the differences between the RCP 2.6 and the RCP 8.5, and displays a sea level rise associated with the 5th and the 95th percentiles. And as you can see, that changes around our coast. The impact on meteorological patterns and wave climate, however, is a very complex picture, and it contains some significant uncertainties. The report explains that there's no evidence for significant changes to future storm surge. Also assessing the impacts on wave heights, it gives a complex picture as well, with increases and decreases in the range of plus or minus 10 to 20%, varying by geographic location and also between the different models that they used in the analyses. So at the Environment Agency, we've taken a measured but precautionary approach to include allowances for sea level rise, wind, wave and surge increases into our coastal models in order to assess the impact of climate change on coastal risk. One thing is for certain though, as we do increase sea levels, we will experience higher energy or higher wave energy reaching our coastline, which will increase the flood risk and erosion risk and test our coastal defences more frequently. The next slide, please. So, I mean, why is all of this important? Being an island nation, we're really exposed to the risks posed by coastal flooding and erosion. We've got approximately 1.8 million homes at risk of coastal flooding and erosion in England. Around 1.8 thousand kilometres of the English coast is at risk of erosion, and approximately 2.7 thousand kilometres is at risk from some sea flooding. And there's a legacy of our coastal towns, ports, industry, energy and infrastructure being sited along the coastal fringe. Much of this is protected and hugely reliant on substantial sea defences and leads to low perceptions of risk along our coast. Coastal risk also impacts on our environment, due primarily to land claim for agriculture and development. For example, we currently have about 15% of the salt marsh remaining when compared to about 150 years ago. And estimates by some coastal managers have previously put annual losses of intertidal habitat at around 100 hectares per year across England due to the ongoing pressures of coastal squeeze. Depending on the effects of sea level rise, we currently expect to lose around 3,000 hectares of internationally important intertidal habitat as well by 2100. There are also, of course, environmental risks such as waste landfills, of which there are over 1,000 known along the coastline, many of which contain potentially hazardous material and plastics. Without our coastal management interventions, the impacts at our coast would be much higher. And as climate change causes sea levels to rise and brings more wave energy to our coastlines, these impacts will only increase and require continued investment and, as Caroline mentioned, more adaptive management. So the coastal models created by the EA are used for a wide range of coastal applications. They're there to provide robust evidence to support flood defence schemes, habitat projects, and provide erosion projections. And that's why coastal risk modelling is so important, and particularly why it needs to account for climate change. On to the next slide, please. So how do we actually apply this in our coastal models? Well, in order for us to add climate change impacts onto our coastal models, we first need to have an extreme sea level data set to provide present day water levels for storm surges. For this, we use our coastal design sea levels from the Coastal Flood Boundary Extremes Sea Levels data set, which was published in 2018. And you can access that as open data just on the internet. And this provides us with annual exceedance probability still water levels around the coast, as you can see on the dots in the map here for parts of the southwest. This information takes long-term data sets from our network of tide gauges around the UK to create the extreme water levels. And once we've got this, it's a simple case of adding the correct allowances from UK CP18 for water level increases onto the extreme water levels. I provided a quick example just in the table there, just to show how you move through that process. This provides the modeler just with a peak water level, and they can then follow the guidance set out in the Coastal Flood Boundaries report to create an extreme tide curve to provide time series water levels for inputs to their model. Wave transformation models are used to bring the offshore wave characteristics to the shoreline, and it's that part of the modelling chain where wave and wind allowances are for climate change are applied to create those increases in wave energy. The wave transformation models are used in combination with the tidal hydrodynamic, wave overtopping and inundation models to assess flood risk. If you can move on to the next slide, please. It's important to note that the impacts of flood risk vary across the country, depending on the geography of the location. On the right here, we can see some of the work done in the Plymouth Coastal Model, which shows the historic Barbican Harbour, and even with its current tidal defences, we can see a large increase in the 200-year tidal flood outline when we project out to the year 2115. Other sites in Plymouth are more vulnerable to wave overtopping rather than this still water flooded risk, and they've got relatively little increases in inundation with climate change increases. In those locations, it's more the increase in wave energy and overtopping that poses the risk in terms of damaging defences, causing structural damage to the built environment and creating hazards for people. In other locations, such as the south coast here at Rye, we see much larger increases in flooding with rising sea levels due to the extensive flat topographies. Next slide, please. As I mentioned, I want to touch on some of the other risk aspects. The English coastline has significant areas at risk of erosion, and it's not only a factor of rising sea levels and the potential for increased storminess, but the impact of rainfall on groundwater and landslides too. So at the Environment Agency, we produce a national erosion risk mapping product called NCERM, which provides us with erosion projections for 10, 50 and 100-year epochs. And that's used to inform local planning and coastal management activities along our coast. The impacts of climate change are included in these projections, and the current update to NCERM will include the influence of the UK CP18 work. Next slide, please. As Caroline mentioned, here's a slide here just on adaptive pathways. So the pressures of climate change at the coast will inevitably increase the importance of adaptive coastal management. This is another coastal modelling activity which is being done by the Environment Agency using the UK CP18 data. And it's used to model future coastal change scenarios and provide powerful visualizations to bring these issues to a more accessible format. The images here are taken from the visualization work for the Bude Adaptive Pathways project, showing 2020 versus 2120, and they use erosion and inundation projections, and they use those to inform coastal managers about risk and management options along our coast. And just onto the final slide, please. So that was just a very quick and brief overview of how the Environment Agency use climate change data in our coastal modelling. And as you can see, coastal modelling is a crucial activity to inform us of the present day and future risks associated with our interaction with the coast. The modelling provides that essential base for us to provide protection to communities, inform appropriate investment and create sustainable plans for future coastal management. Thank you. I'll now hand over to Claire.
Thank you very much, Ben. Can I just check you can hear me?
Yes, we can.
Brilliant, thank you. So thanks, I'm Claire Waller and I'm going to be talking to you about climate change and peak river flows. So we have known for many years now that climate change could lead to an increase in our peak river flows and fluvial flood risk. And back in the early 2000s, we were applying a default 20% increase to all flood flow estimates across the whole country. And it's hard to believe now that that's nearly 20 years ago. But since then, our science and research has become increasingly sophisticated and our climate change allowance system more and more detailed as a result, now varying at the catchment scale with different allowances for different time periods and scenarios, as Caroline indicated earlier. So we're going to start by looking a little bit more at how these allowances were calculated. And I should say none of this is my own work, full credit to others for completing this work. So the EA and SEPA commissioned UKCH to undertake a research project that modelled peak river flow impacts for all catchments greater than 100 kilometres squared area. And the method used there has been published in this paper that's freely available online by Alison Kay and others from CH, and will also be published as a EA Science R&D project in due course as well. And this modelling used the grid-to-grid national scale hydrological model. This model runs on a 1 kilometre squared grid size and at a 15-minute time step. And it has various spatial data sets as input, such as elevation, soil types, and land cover, as well as the daily rainfall and evaporation time series data. And the grid-to-grid model was chosen because it's been shown previously to perform well for a wide range of catchments across the UK. And it's also well established for use at the national scale. For example, it's used for real-time fluvial flood forecasting by the Flood Forecasting Centre. And the image on the right shows an example of the output of the grid-to-grid model. So the data shown here in blue are the 50th percentile of changes in flood peak for the 1 in 20 annual exceedance probability event in the 2080s epoch under the RCP 8.5 emissions pathway, and also for the medium August temperature potential evapotranspiration scenario. And you can tell from the length of that description that there was an awful lot of data generated in this project for many different flood magnitudes and climate change scenarios and epochs, and also emission pathways. So in terms of how we collated and used that data, the results were collated and displayed using these response surfaces shown here on the left. And these were generated for every single 1 kilometre grid cell across the UK with a catchment area greater than 100 kilometres squared. And the colours in that response surface indicate the change in flood peak. So here purple is a very high increase in flood peak, greater than 90%, and grey is very low, in fact less than 0, so a negative change in flood peak. And the X and Y axes here represent the rainfall properties. So the y-axis here is the annual mean change in rainfall, and you can see that it was modelled from a minus 40% change up to a plus 60% change in annual rainfall. And the x-axis here is the seasonal amplitude. And so these response surfaces were also plotted for 3 different annual exceedance probability events, so 1 in 20, 1 in 10, 1 in 20, and 1 in 50, and also 3 temperature potential evaporation scenarios as well. And then they were used to calculate the potential changes in flood peaks for the specific UK CP18 climate change scenarios that we wanted to look at. And they are plotted on here by those blue dots that you can see there. And from those sampling those blue dots off of those response surfaces, we can create cumulative density functions such as plotted on the right here. And then from these, you can read off the changes in flood peak for different percentiles of the distribution. So for here, for example, the 50th percentile of these particular projections at this particular location is about a 20% increase in peak flow. The next step in the process then was to decide how to use these 1 kilometre grid outputs to develop climate change allowances. And here this needed to be a balance between making the most of those very detailed spatial resolution of data available against the need for pragmatism and practicality in flood risk studies. And so we decided to average the results across whole catchment scale. This allows us to give straightforward advice that is easy and quick for our customers and the Environment Agency to apply, compared to if we were trying to use the 1 kilometre grid allowances directly. And we chose to average the results over the management catchment scale that's shown here. It was found that this scale is still representative of the 1 kilometre grid projections in most places to about 10%. On contrast, if we'd scaled up to the larger River Basin district scale that the previous allowances used, this would have masked much of the greater variability in response at the local scale that the latest modelling has shown. On the other hand, if we tried to zoom in closer to the smaller operational catchment scale, too many of those smaller catchments would actually have had no allowances because they fell below the 100 kilometres squared minimum catchment size threshold that was used in the grid-to-grid modelling. We've also chosen to set as our main requirement for flood risk assessments the central allowance. This represents the 50th percentile of the RCP 8.5 scenario for the largest event which was assessed, which was the 1 in 50 or 2% annual exceedance probability flood. And then this allowance is applied in flood risk assessments and modelling studies to all annual exceedance events and to the full flow hydrograph. This allowance represents a high emission scenario and fulfills our requirement to plan for a 4-degree world. So what do these new allowances look like across the country? So this image here shows the central allowance percentage increase in peak flow for the 2080s. And you can see that there is significant amount of spatial variability across the country. Broadly speaking, there are higher expected increases in the west and lower expected increases in the east in comparison to each other. And some of these allowances are really very different to the previous allowances we were using. And in some particular cases, for particular scenarios and epochs and management catchments, the allowances are even negative. And these differences between the new allowances compared to the old allowances are due to a combination of various different things. Firstly, we're using different emission scenarios. So here we're using the high emission scenarios. The previous allowances in some cases used a medium emission scenario. We're also using the new rainfall projections, and in UK CP18 it's indicated that the west of the UK will become wetter and hence this greater increase towards the west of the country. And then secondly, the new high resolution modelling has allowed us to identify peaks and troughs in catchment responsiveness to climate change that take into account not just the changes in precipitation due to climate change, but also other climatic and non-climatic factors, such as different catchment characteristics that affect how sensitive the catchment is to changes in rainfall. And what this has shown is that the link between changing rainfall patterns due to climate change and fluvial flooding is not straightforward. And while precipitation is a major driver of river flows, and we know that there will be more rain overall, more wet days in winter and more extreme thunderstorms in summer, what the modelling has shown is that air temperature, evapotranspiration, and other non-climatic factors are also important. And in particular, this research identified that antecedent soil moisture is key to this relationship. And this means that in the more arid catchments on the eastern side of the country, fluvial flooding does not always increase, and in some cases decreases, despite the rainfall intensity increasing due to climate change. The final topic I wanted to touch on today was how, in addition to the climate change allowances work, we are also starting to adapt our flood estimation methods to recognise the climate change impacts that we are already starting to potentially see in some of our gauging station records. So our standard flood estimation methods assume that our present day flood risk can be estimated using data from the past, typically time series of annual maximum flood peaks, and that those time series are stationary. And that means that their statistical properties, their mean, their median, and the standard deviation do not change over our timescale of interest. But in some gauging station records, we are starting to see possible trends of increasing flows. So the Environment Agency undertook some research on this, and that was published last year. And this research identified that about 13% of river gauging stations now show a statistically significant upward trend in annual peak flows. And as a result, we have introduced new methods for non-stationary flood frequency estimation to be used on capital works schemes. And you can access these methods and the guidance on the DEFRA website at the link shown here. And the graph on the right here shows an example of that type of output. So the grey bars there represent the annual maximum flow observed in each year. The solid green and blue lines show the sort of traditional stationary flow estimates for the 50% or 1 in 2 and 1% or 1 in 100 annual exceedance probability events. And the green squares and the blue squares show non-stationary flow estimates. So as time goes by, your 1 in 100 flood estimate is not stationary, it increases with time in this case. And these new tools are another way that we are starting to address the potential impacts of climate change on peak river flows. So that's it for me. Thank you very much for listening, and on to our next speaker, Mike.
Thanks, Claire. Yes, I'm Mike Vaughan. I'm a senior hydrologist working at the Environment Agency, but specifically on the local forecasting system. So the previous speakers really have been talking about the effects of climate change and what we need to do in terms of sort of planning, building defences, land use planning and the like. But another key strand in all of this is how we actually manage flood events when they occur. And I'm going to talk about some of the implications of climate change for incident management. I'm specifically looking at the effects on flood forecasting, and very particularly the fluvial flood forecasting within the Environment Agency's local forecasting service. But I think it's important to bear in mind that there are other sources of flooding that we forecast. So we include coastal within the local service as well, and more widely, we look at surface water and groundwater, and we have partners with the Flood Forecasting Centre, which is the joint organisation between the Met Office and the Environment Agency, who are involved in this at a more strategic level, as well as providing a lot of the data we use in the local service. And of course, this all sits within the overall flood incident management activities, and this is it's just a part of that overall jigsaw puzzle. So it leads on to decisions about flood warning operations, and the overall management of events. But I'm not going to cover those specifically. I'll also say I'm only going to be talking about England. The Environment Agency only covers England, so I can't speak for the other constituent countries of the UK. And I think overall in this, with there's as many questions still as there are answers, but we'll talk through some of what those are. And I think just to sort of set the scene, when I sort of started thinking about this some time ago, my initial thought was, well, looking at the climate change projections, we're obviously going to be doing more forecasting, but that's about it. But when you start to think about it and look more, there are things we need to do to adapt as well. So, which I'll talk about through the talk. So I'll talk first a bit more about the background to forecasting and how the local service works, look at some of the relevant aspects of the climate change projections, and then what those impacts might be. So Claire, if I could have the next slide, please. So we're saying that flood forecasting and flood incident management is a core part of the National Flood and Coastal Erosion Management Strategy for England, absolutely highlighting the need for timely and effective forecasting to support warning, evacuation, and all the rest of it. So it's absolutely central to how we adapt to climate change. Have the next slide, please. And just look quickly at the sort of the role of real-time flood forecasting. It's very much about providing information on future river flows, river levels, to support decision making by others during flood events. So the timescales are very different to the sort of planning decisions that were talked about earlier today. So really, we're looking hours to days ahead. The local service, we look 5 days ahead. The strategic services provided by the FFC and the Met Office a lot longer than that, but it's those sorts of timescales, and we're looking at sort of what's actually going to happen given weather forecasts, rather than the sort of climatological outlooks we're providing in the sort of the design side, which we've been talking about so far. As I say, it's only one piece of the jigsaw. It sits within the overall flood incident management process. And there's a number of components, both technical around the models and the IT systems and the data that we use, but also people to operate and interpret the forecast as well, are a key part of the system. So cover the next slide, please, Claire. Thank you. So the local flood forecasting service and it's run by the Environment Agency. We're reliant on input from the Met Office and some of that through the Flood Forecasting Centre, who, as I say, both have wider roles. The slide here is sort of a simplified overview, focusing particularly on the fluvial elements of the service. The coastal doesn't look widely different to this, but it's certainly some of the details different. I think that the things to highlight are top left there. We've got the field data, the measurement of river flows, river levels, rainfall by rain gauges, and weather radar. All input into the overall process is absolutely critical to what we do. We take the rainfall forecasts from the Met Office, and some of those are modified by the Flood Forecasting Centre, and that they're fed into the system. We've then got a core forecasting system, IMFS, the Incident Management Forecasting System, which sort of coordinates all the technology. And within that, we have a number of predictive forecasting models which are used to produce the actual predictions of river levels, river flows over the next few hours, next few days. And then those are fed out to people. So in this case, we've got MFDOs, monitoring and forecasting duty officers, who are running the models. I mean, a lot of it's automatic, but doing additional runs, looking at the input data, making sure that's okay, interpreting the results. And then in this case, we're showing it being fed out through an internal web portal to the flood warning duty officers, who are then making decisions on flood warning. But of course, the information goes much more widely within the organisation for the other aspects of flood incident management, and then out to external partners and the public through those routes as well. Next slide, please, Claire. So moving on to the relevant aspects of the climate change projections. So really, I think just looking at it without sort of thinking about too much about the detail, but the broad direction of travel we've got is we're expecting more intense rainfall, more frequent rainfall events, changes to the antecedent conditions. So we're looking at catchments which are drier in summer, perhaps wetter in winter, which can affect how catchments will respond, particularly rural catchments. We're looking at higher peak river levels, higher peak flows, and of course there is that regional variation in this, but that's the sort of the overall picture. Now, in terms of timescales, now clearly these, we're looking at decadal changes here, whereas the forecasting horizon is, say, hours, days, weeks. So we're not so much looking to forecast changes, the effects of the climate changes, but we do need to incorporate what's likely to happen through the climate to make sure that all of our system components can cope with both the changes in the means and the extremes. So the question really is, what do we need to do to adapt to these changes? And I think there's perhaps three areas which are key to this. But Claire, could we move on? Thank you. So the first of these is what do we do about the observed data? So if we're looking at higher rainfall intensities, then have we got the gauges that can measure those higher intensities accurately? And certainly there's some of the newer technology is moving in that direction. But given the increase in convective storms that we're expecting and the lengthening of the seasons, of the convective season, then have we got the coverage of the rain gauge network to measure convective rainfall adequately at the right scales? And clearly there are always going to be difficulties with this, and the radar has a role to play, but do we have a network that can really capture that in the way that we need it to? In terms of observing river levels and river flows, and we're expecting higher peaks. So can the instruments actually measure that? Are they high enough above water levels to measure that? Currently we do get gauges flooded during events. For flow measurement, a lot of flow gauging stations are based upon having a rating curve to convert an observed level to a flow. Do they go high enough? Is the site capable of containing flows sensibly at high enough levels to measure the flows? So there's questions around that. We don't make much use of observed soil moisture data at the moment. We do have modelled soil moisture data, but we don't use observed. And perhaps with the changes we're expecting to antecedent conditions, maybe this becomes more important. That general sort of resilience to bigger events in sort of comms as well as the gauges themselves, we've got to think about that, making sure we're getting the data back in a timely manner when we need it. And all of these are really long-term investments. You don't sort of keep changing the gauges every few weeks, every few years even. So although there is some scope for managed adaptation in the approach to being able to observe higher flows, it's perhaps limited. So next slide, please. Thank you. And the second area is the forecasting models themselves. So we've currently standardized on 2 model types within the local service. So for rainfall runoff models, which are being driven with rainfall and evaporation and which predict river flow at a point, we use the PDM, the probability distributed model. which is a series of lumped conceptual storages and which are parameterized, and the flows between the stores are parameterized as well. And we've got something like 1,300 of those across the country. And there's a number of questions that arise from this. So, are the processes that are in the PDM, are they applicable under future climate conditions? So, particularly thinking perhaps about changes to the range of soil moisture and the linkages of that to the runoff proportion of rain that runs off. They're also reliant very heavily on past data to calibrate models. So can we use the past data to calibrate for future conditions? And I think there's questions around that. And as well as how well do the models work under those more extreme conditions, and if we're extrapolating the performance to higher flows, higher rainfalls, and all the rest of it. So there's questions, I think, around how the rainfall runoff models, are they suitable for the foreseeable future? And then the second type model class is river routing, for which we use Flood Modeler Pro. And we've got about 500 of these across the country. They're either 1D hydrodynamic model solvers, or in some cases Muskingum routing, or a combination of both. And they're driven with observed or forecast river flow and perhaps tidal levels at the lower boundaries, and then predict river levels and flows directly at that number of points within the models. They're more physics based than the conceptual models that we use for rainfall runoff, so probably more adaptable, but they still clearly need to be able to handle those bigger flows and levels, both in terms of the schematization. So can they cope with a flow that's with the higher flows we're expecting to see, or are those out of the range that the model can deal with? Is the model robust and resilient? Is it in terms of the numerical scheme to solving these higher flows and probably greater rates of change that we're expecting to see in the future as well? As well as that, I think there's a general need for improving accuracy. We don't do too badly now, but if there's greater demands on the service, then we need more accurate outputs. And probably there's a need for new services as well, extend the coverage of the existing service. It doesn't cover everywhere within the country, and perhaps some additional services as well. And so there's some thinking to be done about whether these are the appropriate models to support those services. But I think that there's also a wider question as well around some of this stuff. There's a lot of things going on here. So is this just noise, or what do we actually need to do that's going to make a difference, or is this just noise within the overall scheme of things? But I think with the models overall, the managed adaptive approach is largely possible, but we do need to do some underlying science to lay the groundwork for that. And then looking at some wider considerations, there's a couple of areas. So we can reasonably expect the frequency of operation to increase and costs therefore to go up with that. And also carbon emissions. So the agency has a net zero goal by 2030, and forecasting itself generates carbon emissions through operations, through the operation of computing systems, as well as through some of the installation and maintenance of the gauges which are required. I mean, not just for forecasting, but they're there. But equally, potentially, it can be used to reduce others' carbon emissions, perhaps by better targeted pumping and the like. So there's swings and roundabouts here, but there's certainly some. Perhaps we can think of these as constraints on how we might adapt the forecasting service. And then if we could have the final slide, please. So really, just to sort of conclude and summarise, I think there are some clear requirements for adapting the forecasting to climate change, particularly around observations and some aspects of the modelling. Some of it can be done through a sort of a managed pathway approach. Even there is some groundwork required. There are some technical challenges, but I think at least some of these are likely to have been addressed elsewhere, so we need to explore that more fully. And there are, as I say, some constraints around costs and needing to reduce the emissions of the forecasting work itself. Now, I suppose the good news is that there's work underway in most of these areas. Currently, there's work ongoing, and we're also developing an improvements programme for the next few years, which will look at a lot of these issues, learning from others, introducing some innovative approaches as well. So there's work going ahead, but I think there's potentially quite a lot to do here. And just finally, some reminders, as I say, there are the other sources of flooding: the coastal, the surface water, groundwater, the other organisations, the Flood Forecasting Centre and the Met Office and other professional partners, and that wider flood incident management context of warning and informing and actually managing the incident as a whole, not just forecasting, although it's clearly the forecasting is a core point. So I think that's about it from me.
Thank you very much, Mike, and obviously thanks to all the presenters this afternoon. Barbara, do you have a few words to say specifically on CIWEM, and then Jane can pull together some questions?
Hello there. Just to say thank you very much to the speakers. Very interesting presentations. I hope that I kept up with the links. I was trying to do it as quickly as possible. Really just to highlight the work that CIWEM is doing on COP26. I'll just copy and paste in the link to our countdown to COP26, which is on our website. So I just copied that in, and basically we've also got some CIWEM talks COP26. So we've got various people within our organisation and members who are actually what they would like to see happen at COP26, and I would certainly urge you to have a quick look on the page. And there's just one event that I would perhaps highlight, which is coming up in November, so in a few weeks' time, which is the Urban Drainage Group's Virtual Annual Conference and Expo 2021. And again, I put the links I popped in the chat if you're interested in that. But thank you very much again for your speakers, really interesting. And let's just hope that COP26 delivers what we all need it to deliver.
Great. And if the speakers don't mind popping on your cameras and microphone, because we'd be happy to have anybody jump in on any of the questions that the audience has for us today. Thank you, audience, for submitting questions. And also, there was a lot of chat between the speakers and the audience about some of the questions as well. So do take a look at both Slido and the chat to catch those. But I'll do my best to capture that in the time that we have left. First of all, I personally would like to say thank you to Lizzie for introducing the idea of having that final slide being my personal carbon pledges. I think that's a really just simple yet creative and powerful message, and I'm hoping we can start a little movement here. I'm definitely going to jump on and encourage people at CIWEM to do the same, so thank you for that. Great. So we've got a couple of questions in here for Lizzie. So it was kind of a technical question, and you did answer this to Charles in the chat, but maybe for the benefit of everyone in case they didn't catch that, does a run for the time slice 1980 to 2000 refer to matching the statistical characteristics of climate during that period rather than the weather?
Yes, so I think it's important to distinguish between these climate projections and what you'd traditionally see in a weather forecast. So a weather forecast is an initialized forecast running out for a few hours. So it knows the observed state of the atmosphere and it has a simulation of observations in it. Whereas when you run a climate projection, you don't have that information tying it closely to the observed state. So a particular date in the model simulation, as I've tried to answer in the chat, doesn't correspond to reality. But what we do think should correspond to reality is kind of the accumulated statistics of events over time. So, you know, weather events as they would occur on a sort of typical types of weather events we'd experience, you know, what sort of distribution of rainfall intensity would expect over a period of time. But it's important that people understand the distinction between climate projections and shorter term weather forecasting. It's quite different.
Right. Thank you. And this might be a question for everyone at the EA, although I did notice that Ben did address Amanda's question in the chat. So how can we assess future flood risk when EA flood maps don't always include the impact of climate change? Does anybody want?
So yeah, I can take this one. So yeah, the flood maps currently don't take into account climate change, as you've rightly pointed out. So we include climate change in our more detailed local models. So if you need to try to work out any of those climate change impacts, get in touch with your local area Environment Agency teams. They may well be able to help you with that. From a development point of view, we do ask developers to look at climate change impacts, and so that's down to them to model those climate change impacts. And work is in progress to look at our national flood risk assessment so that we can include climate change in the future.
Great, thanks, Ben. Anybody else want to come in?
Hi, it's Caroline here. I'll just add that as well, local authorities, as part of their evidence base for their local plans, they produce strategic flood risk assessments. And if they're allocating areas at risk of flooding, then they'll have to do a level 1 and level 2 flood risk assessment, a strategic flood risk assessment, which should assess climate change as well. So if they should provide a good source of strategic flood risk mapping information as well.
Great.
Providing they're up to date.
Thank you. So a question from Holly here for Lizzie, I believe, although anybody's welcome to jump in. How do we ensure that we can consider these changes in weather and flood forecasting? Will these projections inform updated climatology for NWP?
Okay, so interesting question. So obviously forecasting is on the time scale of a few hours. As I said, and here we're talking about climate projections on much longer time scales. So, we wouldn't expect the influence of climate change to be visible in the short range forecasts. Obviously, as we progress through time, the climate signal will be emerging in what we actually observe on a day-to-day basis. But my understanding is that baseline essentially will be seen in the forecast through the assimilation of observed conditions as going into it. So the climate models are telling us that the frequency with which we expect to see these events will be increasing. And that's something that we need to build into our risk assessment frameworks. But in terms of short range NWP forecasting, I think that's quite a different situation than actually what we're trying to look at here in terms of climate projections. So it would be more the kind of changing climate will be felt in the baseline state that is then used and simulated into the framework of the forecasting system. I hope that answers the question, or maybe I've misunderstood it, in which case please elaborate.
Oh, well, we have Holly on the panel actually, so if you want to jump in, Holly, please do.
Yeah, that's perfect. That's fine, thank you.
Great. We've got another question from for Ben, but maybe for everyone from the EA. How does the EA balance the issue of committing to caring for coastal sea defenses over a scale of 50 years when budgets are sort of agreed in a much shorter time frame?
Yeah, thanks, Charis. This is a really good question. So thanks for posting it. Just because a sea defence is there now doesn't mean that would be the most appropriate way for us to manage risk in the future. So that's the first thing I would point out. Obviously, it's very difficult in that sense, and we can't really plan for investment levels and funding to that sort of 50 years plus sort of timescale. So what we do with the coastal protection authorities and ourselves is we produce shoreline management plans, which look at those future epochs and look to see how we'd like to manage the coastline in the future. And we use those as a tool for that coastal management perspective. On a shorter term, year-to-year timescale, we obviously do have maintenance programs and reactive measures in place just to direct resources where they're needed.
Great. Thank you. And I think we are unfortunately at 2:30, even though I feel like we could talk about this some more. So thank you, everyone, for your great talks today. Really informative. And thank you to the audience, too, for your active participation. We will be posting the recording of this session up on SciWim's YouTube channel, which is youtube.com/SciWimViews. So feel free to check that out. And I do believe Barbara has posted that in the chat. And unless the panel has anything else to add, I think we will close the session for today. Great. Thank you, everyone.
Thank you all.
Thank you.
Thank
Bye.
you. Goodbye.
Thanks a lot. Bye-bye.